Okay, so here we're going to take a look at a different type of improper integral. All right, so for this particular one, right, we have some kind of discontinuity either in one of three places, right? Either at the endpoints, right, the right endpoint, as we see in our definition here from our book, on the left endpoint, or somewhere in the middle between A and B, right? So the function is continuous essentially either everywhere except the right endpoint, the left endpoint, or somewhere in the middle, right? So something like this is going on, right? Where this continuity happens at the endpoints, right, or somewhere in the middle. Okay, now the idea is the same, right? So what we do here is we approach these limits, right? If it's on the if it's on the right, then we look at the left side of the limit as I approach it. If it's on the left, we look at the right side of the limit as I approach it there. Okay. All right. And then here, if it's somewhere in the middle, then we split it up as we've done before, and then it becomes one of the first two cases there, each one of these. All right, if we look here, right, if the value C is somewhere inside AB, then we split up the integral at C, and then part 1 and 2 of the definition applies. Okay, so now let's take a look. Let's take a look at one where the discontinuity is at the end. Right. So we'll take a look here at the integral from 0 to 2 of z squared ln of z dz. And the function, the natural log, is undefined at 0. Right? If we recall the graph here, the ln looks like this, right, where that's 1. Okay. And then as it goes to 0, it is not defined. The function goes to infinity. All right, so we're going to look at this, the limit as t goes to 0 on the right side. Okay. All right. And everything else, so lower limit now becomes t, upper limit now becomes 2, all right, or stays 2, and then we have z squared ln of z dz. All right, so a limit like this I'm going to do using parts. All right, so choose one to differentiate, one to integrate. So differentiate ln of z, integrate z squared, and I'll just do it once, then I'll rewrite. All right, and again, the reason just once, well, we see that once there's no more natural log, then I can easily integrate the resulting function here by using the power. So the limit as t goes to 0 on the right from t, excuse me, so we get z cubed over 3 ln of z, and then minus the integral here of what turns out to be z squared over 3 dz. All right, and now I can do that last one, and that goes from t to 2 using the power rule. So we get the limit as t goes to 0 plus of z cubed ln of z, and then this becomes z cubed over 9 by using the power. Add 1 that gives me a new power of 3, divide by the power of 3 again, and evaluate it from 2, upper limit 2, lower limit t. Right, so when I plug in 2, right, we get 2 to the third is 8 thirds ln of 2 minus 8 ninths, and then minus, and here's where I'll rewrite the limit. The limit as t goes to 0 from the right here. Now when I plug in, so t, so we get t cubed over 3 ln of z minus t cubed over 9. All right, now the part without the natural log, though, excuse me, that should be ln of t. right? So that goes to 0, right? That's that one right away. I can just plug in that 0, so it goes to 0. So I'm going to focus on this other part of the limit, right? So the limit as t goes to 0 on the right, and here I'll bring out the 1/3 on the outside. I really just care about these quantities here. T cubed times ln of t. All right, and we see that this, I'm going to be able to apply L'Hopital's rule, right? Because as t goes to 0, this goes to 0, but that goes to infinity, right? So it's not quite in the indeterminate form, but with some algebraic manipulation here, we'll get ln of t over t to the negative 3. And now it is of the indeterminate form. Right now we have infinity over infinity. Okay. All right, and now applying L'Hopital's rule, we get 1/3 limit as t goes to 0 from the right, and the top becomes 1 over t, and the bottom becomes negative 3 t to the negative 4th. Okay, and now we're going to clean this up here. And here we get 1/3 limit as t goes to 0 from the right. T to the 4th comes to the numerator, but then the t, this one comes to the denominator. All in all, we get negative 1/3 t cubed. All right, but that all, now I can just plug in 0. That all goes to 0. So we're left with 0. All right, so as it turns out, this whole limit goes to 0. And what that tells me is that we're left with this quantity, right? A finite number, right? Whatever the number is, right? The fact is it's finite, so the interval itself converges. All right. Okay, and that's how we do something here that is not continuous on one of the endpoints. All right, now let's take a look at this example here. From 0 to 3 of dx over x squared minus 6x plus 5. Okay, and okay, so once again, we'll start off here. I'm going to factor the denominator just to get an idea of what's going on here, right? So x minus 5, x minus 1. Okay, and then we notice here that this function itself is undefined at 1. All right, when I plug in 1, I get 0 in the denominator. All right, so that means that I'm going to split this up. Go from 0 to 1, dx of x minus 5, x plus 1, plus 1 to 3. Of dx over x minus 5, x minus 1, Okay, now this looks like I'm going to need the method of partial fractions, right? So I want to, again, set up my method here. So a, x minus 5 plus b over x minus 1. Okay, and again, I won't go through this whole process here. There's a video up in a previous week where we went over the partial fractions, but I did all that, and as a result, I got 1/4 over x minus 5 minus 1/4 over x minus 1. Okay, so now I'm going to start with the first one here from 0 to 1. So here, there is a discontinuity at 1. So the limit as t goes to 1 from 0 to 1 of 1/4 x minus 5 minus 1/4 x minus 1 dx. Okay. This this is t up here, excuse me. All right, so now here we'll have, I'm gonna factor out the 1/4, just bring it all the way out here, right? And each one of these is a natural log, absolute value of x minus 5 minus natural log of x minus 1, evaluated at t and 0. So when I plug in, again, 1/4, right, ln of absolute value t minus 5 minus ln of t minus 1. And then when I plug in 0, we get minus ln absolute value of negative 5 minus ln absolute value of negative 1. Okay, now that goes to 0. Ln of 1 goes to 0. Ln of the absolute value of negative 5. So ln of 5, that's just some constant. So that one's okay here. And oops, I forgot my limit. Limit as t goes to 1, and here when it's on the top, it should be on the left side. Okay. All right. Now, if I plug in 1, I also don't have a problem with this quantity here, right? So when I plug in 1, this is ln of absolute value of negative 4. So that is also okay as well, right? The only issue is here, right? So when I take a look at this, the limit as t goes to 1 on the left, right, of absolute value of t minus 1. Okay, so what we see here is that as t goes to 1, this quantity is going to 0. And from earlier, when we were kind of here, we were talking about the natural log, right? Those values, as I get closer and closer to 0, go towards negative infinity, right? So what happens here is that as t approaches 1, right, these values are going to 0, right? So this whole thing is going to negative infinity. So it diverges, right? Now, the fact that these other values are constant really doesn't matter, right? One of these parts is going to negative infinity, so the whole integral, I don't even need to worry about the second part, right? Because it may or may not converge, but at this point it really doesn't matter because part of it diverges. So my whole integral that I started with, this one here, is divergent. Okay, remember, in order for convergence to occur, they both must agree, right? There won't be a value that is going to balance it out on the other end.